This presentation is titled NOAA's Future Geostationary Imager. My name is Dan Lindsay from NOAA NESDIS. I'm the GOES-R program scientist, and I'm also serving as the instrument scientist for the GeoXO Imager, which is the topic of this presentation. This work is a group effort. Contributions from several folks are listed below. This is really not everybody. It would be impossible to recognize everybody who is helping with this effort. This chart shows a brief history of NOAA's geostationary operational environmental satellites. You can see that it goes all the way back to GOES-1 in the mid-1970s, and the one instrument that's been common to all of these series of satellites has been the imager. With GOES-16, the current series flying, we had a significant improvement with the advanced baseline imager. And so right now we're planning for the future series that will follow the GOES-R series to be launched in the early 2030s, and that's known as the GeoXO program. In addition to the imager, we're looking at adding or having improved lightning mapping, day-night visible imagery, infrared sounding, ocean color, and atmospheric composition. However, the focus of today's presentation is just on the imager. You'll see the acronym GXI to represent the GeoXO imager. The Geostationary Extended Observations, or GeoXO program, is not yet formally approved, but Phase A studies with industry have begun on the future GeoXO imager. The ongoing studies are looking at a set of GXI baseline requirements, along with some potential additional requirements that would constitute even further upgrades in observational capability. So this presentation is going to highlight the baseline and priority GXI requirements currently being studied and discuss some of the observational motivations for the improvements being looked at. I plan to show several charts that look sort of like this. This represents a list of the spectral channels that are being looked at for the GXI. And the first one here is what is our baseline. So this is sort of what the very minimum that we're going to shoot for in terms of the capabilities of GXI. And you may recognize that many of these bands are quite similar to what we have currently on the advanced baseline imager, with a couple of important differences, and those two are highlighted here. The first is the addition of a so-called green channel near 0.55 micrometers in the visible, and the second is an improvement of the 3.9 micrometer channel from a 2 kilometer at nadir resolution down to a 1 kilometer at nadir. So I'll look at examples of each of these improvements. The first is the addition of a green channel. So ABI lacks a green channel. It does have blue and red, does not have a green channel. But some groups have made an attempt to simulate the green component in order to make true color imagery. And it really works pretty well, but there are some instances where it fails. This example here comes from Sierra's GeoColor product. You can see what is very strange looking colors within some smoke and clouds off the western coast of the US, which is clearly an error, and that's directly related to a poor attempt to simulate the green component. So having an actual green channel will solve this problem. It'll allow us to make the true color imagery properly, but perhaps more importantly, it'll make it easy for everybody to do that. You won't have to go through the process of simulating a green band, and it'll make it easy for all users. True color imagery has proven to be extremely useful for forecasters, mainly for aerosol detection, situational awareness, and public outreach. So it's not all about pretty pictures. It actually does have some operational utility. Note that the center wavelength is 0.55 micrometers. That's similar to the VIIRS instrument, as opposed to 0.51 micrometers, which is what Himawari AHI has. And the reason we did this is to get more in the area where we have correct green reflectance off of vegetation. And so it really does provide a better green in the true color RGB. In terms of the improved resolution of the 3.9 micrometer channel, the 3.9 channel, as you probably know, is the primary band for fire detection. A resolution improvement from 2 to 1 kilometer will allow detection of fires 4 times smaller, and that increases the chances of early detection. And it'll also allow better tracking of rapidly changing fire lines. And the example on the right here was provided to us by Jason Apke of Sierra, and shows the fire temperature RGB simulated from a fire called the Caldor Fire, which is burning in California the second half of August 2021. And you can really see at the pixel level how good a resolution we can see, and we note that the fire is advancing rather quickly to the southeast. So this is simulated 1 minute data along with the 1 kilometer resolution. The next set of requirements, these are potential upgrades. We have put into three priorities, priorities 1, 2, and 3. I'll show them individually. Priority 1 is shown first, and there's a few more improvements highlighted. The first one is with that fire detection ban, we would like to increase the saturation temperature up to 500 Kelvin. Right now with ABI, it's just over 400 Kelvin. So an increase to 500 Kelvin would allow better fire characterization and decrease the chances that you get saturated pixels. The second improvement highlighted here is an improvement of the VIS 0.64 band from 500 meters currently with the ABI up to 250 meters. And the goal here would be to better resolve features such as developing cumulus clouds. This example shows what the really high resolution 250 meter visible might look like. This is on the left is a Landsat 8 band 3 image at really high resolution, and that data was used to simulate what 500 meter data in the middle and then 250 meter data on the right would look like. And the main thing to note is you get significant improvement and less blurriness on the right compared to the middle. In terms of applications, as mentioned on the previous slide, we think that the biggest advantage of doing this would be for tracking clouds qualitatively. For example, with small cumulus clouds before storms have formed, they tend to be rather small in scale. And for 500 meters, sometimes they get blurred together. But at 250 meters, we should be able to track the individual cumulus clouds as they build and sometimes form into storms. And forecasters will be able to use this data qualitatively to do a better job of forecasting convective initiation. Let's move now to the priority 2 improvements. There's two that I would like to highlight here. One of them is adding a 0.91 band. This is for better detection of low-level water vapor. The FCI imager, which will fly aboard EUMETSAT's MTG satellite, first MTG satellite, does have a band at 0.91. And the 5.1 micrometer band we would also like to add. This is in the water vapor absorption region in the infrared, and is really better for low-level water vapor, which I'll highlight in a couple of slides. In terms of the 0.91 water vapor channel, the chart here from a paper from Barducci et al. In 2004 shows the atmospheric transmittance in the vis and near infrared regions of the atmosphere. As you go further down with the plots, you get less transmittance, and that's due to water vapor absorption. So the two areas that are highlighted, the first on the right is the 1.38 area, or around 1380 nanometers. And this is where we have our current ABI band 4, or the 1.38 band, which we call the cirrus band. And the reason is because the solar radiation that is going down to the surface and trying to reflect back to the satellite gets absorbed largely by the water vapor, so that all that you're left with is a signal from cirrus clouds. But if you go to the left, you can see that there are several other water vapor absorption bands, including near 0.91. And the important part here is that it's less strong. We get more atmospheric transmittance around 0.91 relative to 1.38. So what that means is we can use this 0.91 information to tell us something about the water vapor absorption, specifically in the low levels, because that's where the majority of the water vapor actually stands. This example is taken from a paper by Grosso et al. In JGR back in 2018. This is an example over Mexico. On the left is shown the 0.64 visible band to show that in the center of the image in the Chihuahua region of Mexico, where it's rather elevated terrain, it's completely clear skies at this time. And what's overlaid there is the total precipitable water from a model, and it's showing a 0.25 centimeters, which is very, very dry. And the point here is that it's so dry that we can take a look at the 1.38 micrometer band, a loop shown on the right. And even though this is supposed to be the cirrus band, since it's so dry, we can see all the way down to the surface. So the 1.38 micron radiation is reflecting off the surface and coming back. Throughout the majority of this loop there in the center of the image in Chihuahua, is clear. With the exception of a few bright pixels, those are actually cumulus clouds that start to form. But you can see these plumes of gray areas moving from southwest to northeast. That's not clouds, that's actually dry air with little darker areas in between, which is relatively moist air. So what we're able to do is track these dry plumes, or alternatively track the dark areas, which are the moist plumes. And that can be really useful for forecasters for tracking low-level moisture before storms and anticipating when cumulus clouds are going to form. If you look really carefully, you can see that the cumulus cloud lines do form along those black areas, which are the plumes of the moisture. Now, with the 0.91 band, we don't have to find a really, really dry atmosphere for this to work. It'll work everywhere because there is less atmospheric absorption from water vapor, but just enough to still give us a signal. And so that's the advantage of adding the 0.91 is forecasters can use this information to detect and track low-level water vapor. The second band in this priority that we wanted to highlight was the 5.1 micrometer band. The plots on the right are vertical weighting functions. This is courtesy of some work by Nate Miller and Matt Gunshore from SIMS. On the right shows using a mid-latitude summer sounding what the weighting function of our current ABI band 10 or 7.3 micrometer band would look like. And you can see that it peaks there around 500 millibars in the mid-troposphere. Forecasters really need more information about the lower level water vapor. So even though we call band 10 the so-called low level water vapor band, we would like to see further down than that. And so one way to do this would be to add a band at a shorter wavelength at 5.1 micrometers. And so that's what's simulated on the left, is if we did have a band around centered at 5.1, it shifts the weighting function downward, peaks closer to about 800 millibars in this particular case. And that would really give forecasters some useful information about that low level water vapor. And lastly, the final priority of improvements. These would be the most difficult to attain, and therefore are the lower priority, are listed here in the chart. And everything in bold is an improvement over priority 2. There's quite a bit on here. I'll highlight mainly the addition of 3 bands, 0.41, 0.443, and 1.24 micrometers. These would all help characterize aerosols. Also notice that the resolutions on the right of all of the vis and near infrared bands are 1 kilometer or better in priority 3. Notice that we've improved the resolution of the 6.95 band, which is our so-called middle level water vapor band on ABI, from 2 kilometers down to 1 kilometer. And the reason that 5.5 is listed there is it's indicated that we could also shift this band down to 5.5 micrometers in order to make it a little easier to improve the resolution. The weighting function in that case would end up being about the same as 6.95, which is the reason that it would be considered a replacement. And then lastly, toward the bottom, we would really like to improve the resolution of the 10.35 micrometer window infrared band down to 1 kilometer. So again, all of these things are being studied as part of the Phase A activities. In summary, the Phase A studies by industry are underway, looking at possible designs for the GeoXO imager. Some improvements over ABI are being considered. And then lastly, I'd like to point out that data from partner instruments, such as EUMETSAT's FCI, as part of the MTG series, will be extremely useful to better understand observational value. Thank you for your attention, and I hope that you're able to come to the EUMETSAT presentation itself and ask questions there. Thank you very much.